When I'm doing DSP designs, I always start out with big old floating point numbers. That way, none of my calculations get too upset when I try to multiply by 7.38649899123 times 10 to the minus 16 power by the square root of 6.02 times 10 to the 23rd. Wait, wasn't that some kind of chemistry thing? And doing everything in double precision floating point works just fine in the land of unicorns and rainbows, but here on planet Earth, we eventually hit the reality of doing DSP with an actual embedded processor, and without infinite time and power to finish our calculation. That means we're gonna need to use, you might want to sit down for this, fixed point math. Hi, I'm Amelia Dalton, host of Chalk Talk. I know, come on. Open your eyes and stop chanting, unicorns are real, unicorns are real. It won't be that bad, because guess what? My guest today is Pushkar Patwardhan from Cadence Design Systems, and we're going to make easy work out of those fixed point DSP calculations. Watch us go. Zoom. And before we get started, don't forget to click that link. There you can find out more information about Cadence Design Systems' fixed point DSP solutions. Hi, Pushkar. Thank you so much for joining me today.
Thank you. It's great to be here.
So we're talking about DSP today, but that's quite a lot to cover. So give us an overview on what exactly we're going to be talking about today.
So when we talk about DSPs, we talk about fixed point DSPs, floating point DSPs. So today let's take a look at what DSP applications need from the DSP. So when we talk about computations and DSP applications, this is the application space that we are talking about, from low compute to high compute. So on the low compute, you have variable processing going on to speech and audio processing, radar, and then on the high end, you have the communications modem processing and the vision processing. So the DSP application space spans from low to high compute. But what's common in most of these applications are the compute kernels of the DSPs.
Oh, okay.
So we are talking about filtering, we are talking about FFTs, and these kernels do a lot of math. So when we talk about doing math, we are talking about number crunching, we are talking about multiplies, divides. So in doing math, the two key aspects that need to be considered are how fast can we do the math, how many operations per second, and then the accuracy of the math. What type of numbers and what type of number representations will be used in the computer, the so-called computer arithmetic, when the math is actually done.
Okay, so all of this number crunching we're going to do, when I'm just doing it in software, it's all floating point. But once I start to care about performance and power, it's not all about floating point anymore, right?
Yes, that's correct. Let's take a look at the number representations before we directly address that question.
Okay.
So when we talk about number representations, there are a number of ways in which computers can manipulate numbers. The common ways are to use a fixed point representation or a floating point representation. And in a fixed point representation, there are a number of choices for word width, whether it's going to be a 16-bit representation or a 32-bit one. The key aspects to keep in mind is what is the range of the numbers that can be represented, and what is the resolution, or the accuracy or precision, so to speak, of the numbers that are represented.
Okay.
So in the fixed point case, as we see here, there is a part to represent the range, the signed integer part, and there is a fractional part which represents the resolution. So that's the fixed point number representation, which is commonly used. The other commonly used representation is the floating point, which is a mantissa and an exponent representation. It can use the same 32-bit word, but how the different parts are used is different. And in floating point, IEEE has standards for a 16-bit floating point, a 32-bit floating point, and a 64-bit floating point. So in a floating point representation, the range and the resolution that can be represented is different from the fixed point. In particular, the range of floating point is much higher compared to the same word width of the fixed point.
Okay. So, Pushkar, I can't just randomly pick some fixed point precision, right? How do I know which one I want?
Right. Let's summarize the fixed point and the floating point in terms of what they offer. We said we look at dynamic range and the resolution. So fixed point typically has a limited dynamic range, and in terms of precision, there is a trade-off. Since the same word width is used, if you have high dynamic range, then you have less precision, and if you have lesser dynamic range, then you have more precision. In floating point, you maintain the same precision for a large dynamic range. But what does this precision really mean? And this, as we see here, think of audio. The two in the blue color, the blue graph shows two tone signals. And the noise floor that you see here is basically the quantization noise that comes into picture when you have a number representation. If the precision is less, which is represented in the blue graph, the noise floor is higher. And if you are thinking audio, that's going to give an audible noise or an audible hiss when you hear to audio which has a higher noise floor.
Okay. I am an expert on noise floors from that flat I had in college on the first floor. Oh man, Pushkar.
Yeah, that's right. Having high noise in an audio signal is quite uncomfortable. So we want to push that noise floor down, and the way to do it is to increase the resolution, that is, increase the precision of the number representations. And when you do that, you see the red graph where the noise floor is pushed down, where it's now no longer audible.
Okay, so let's back up a little bit. How did we get here? Where did this fixed point, floating point business come from?
So let's take a look at a typical history of how floating point and fixed point number formats have evolved.
Great.
Fixed point usually has dominated the high volume DSP market, typically low-end DSPs or consumer DSPs, which need very efficient processing, which need to be consume less energy and as less cycles as possible so that the DSPs can run at a lower clock speed. So for such DSPs, fixed point has traditionally been the number format of choice among DSPs because fixed point can consume lesser number of cycles and can consume lesser energy when fixed point is actually implemented in hardware.
Okay.
When you go to floating point, people usually think about high-end computing. You usually think about GPUs, where you need floating point performance and floating point math for all those high compute needs. And floating point is also easy to program. Most of the development platforms that you get default to using floating point, and they have a wide dynamic range. So when you're programming using floating point, you tend to worry less about whether your numbers are going to saturate or overflow. The dynamic range is large enough that you don't have to worry about those things. Due to these reasons, floating point was usually thought of as high-end compute need, whereas fixed point more of a low-end compute need. However, this has changed, and today fixed point as well as floating point are both typically needed in DSP applications.
Okay, so Pushkar, what kind of applications are we really talking about here?
Let's take a look at some DSP applications. In audio processing, the converters, the ADCs and the DACs are typically 24-bit. They may go higher, but that's the kind of range of the converters which gives an audio signal which noise floor is very low that it's not audible. When you have such a signal coming in, it's natural to use 24-bit or 32-bit fixed point processing for processing the audio signal. However, there are some algorithms like IIR filters and room equalization, loudspeaker equalization. The algorithms are best done in floating point because they need higher dynamic range in their internal data representation.
Okay.
So you see in audio processing, there are parts of the algorithm which are nicely done in fixed point, and there are parts of the algorithm which are done in floating point for the same audio application. Let's look at another one. Let's look at communications baseband processing, the processing that happens in your baseband modem. Here, the converters are typically lesser. They are 16 bits or sometimes fewer. So most of the processing for this application is done in 16-bit fixed point. However, there are algorithms, especially the so-called MIMO algorithms, which are used in the multiple antenna processing, which do need floating point for them to be more effective. For vision processing, as well as for radar and ADAS processing, we see a similar trend where a part of processing is best done fixed point, but other part of processing is best done floating point depending on the particular algorithm needs.
Okay.
So most DSP applications need a mix of fixed point and floating point to be done most effectively.
Okay, so let's dive into some details. You mentioned ADAS?
That's right. So let's look at a typical radar application. A typical radar signal processing flow looks like this. Let's look at each part of the processing flow. The part shaded in green, the beam forming and the range Doppler FFTs, that processing is typically done in fixed point using either 16 bits or 32-bit processing.
Okay.
And the reason for that is that the signals that these modules process come from the converters, which are limited in resolution. And so these algorithms, when implemented in fixed point, give a better energy profile and a better cycle performance when compared to floating point. The detection module needs higher resolution, it needs higher precision. It's typically done in 32-bit fixed point. And the direction of arrival algorithms, the so-called DOA or direction estimation algorithms, they need a lot of matrix and linear algebra computations, which are very sensitive to data precision, and it's very difficult to predict the dynamic range of the numbers when these algorithms are used. So these are best done in floating point. So you see in this radar signal processing application, parts of the algorithms done in fixed point and other parts of the algorithms done in floating point.
Gotcha. Okay. So you got another application?
Yes, let's look at communications baseband processing.
Okay.
So here we have a typical processing flow for an LTE baseband modem processing the data channel. The data from the RF interface, the converters, in this case is usually 16 bits or lower. So the upfront modules, the FFTs and the channel estimation, they are best done in 16-bit fixed point, so that again you have a better energy profile and more efficiency in cycles compared to floating point. However, as you go down the processing chain, when you come to MIMO detection, you need higher precision and you need better dynamic range characteristics. So MIMO algorithms, the multiple antenna processing algorithms, are best done in floating point. In baseband processing, once you have processed the signals and once you have come to the point where you are going to detect the user bits, you actually go down. So you go down from using high precision to soft bit processing, where actually you do a lot of 8-bit processing and 8-bit computations. And so eventually, once you do the forward error correcting code, the decoding, you actually end up with user bits, which are of course raw user bits. So the FEC processing is usually 8-bit or sometimes even lower. So you see in an LTE processing application, we again see the spectrum of number representations. You use fixed point and you use floating point.
Okay, cool. So what qualifies you guys to talk about this stuff?
So Tensilica processors cover all the broad range of signal processing applications that we just saw. We have over 4 billion cores shipping annually.
4 billion? Really? That's wow. I probably have one with me right now.
Yes, we have lots of cores covering all the range of signal processing applications, from mobile and wearables to automotive, communications, and vision.
Okay, so we've talked about a wide range of applications, but let's split those up into some categories and talk first about the ones that need to use a tiny amount of power, say my fitness monitor, my wearables.
So we talked about processing for wearables from all the way from a low compute to a very high compute for vision and communications. So let's see how the DSPs cover all that range. For wearables processing, you basically need a low compute DSP, but with good energy efficiency and good cycles efficiency. So for wearables processing, Tensilica has the Fusion F1 DSP. Let's look at its VLIW, the very large instruction word, and its vector SIMD, single instruction multiple data, capabilities. It's a 2-slot VLIW machine, so it's a narrow machine with a relatively narrow SIMD. The narrow SIMD is because the wearables usually need low compute. However, VLIW and SIMD let you achieve the parallelism needed in processing so that you can minimize the energy consumption.
All right, so let's kick up the performance level a notch. Where do we go from here?
Yes, let's talk about audio processing.
Okay.
Audio processing needs more compute than variables. So for audio processing, Tensilica has the HiFi processor family, the HiFi 3 and the HiFi 4. The HiFis are 3 and 4 slot VLIWs, so they are wider. Their SIMD is higher and their the multiply throughput for fixed point as well as floating point processing is higher than the Fusion F1. So the HiFis are targeted for audio processing where the compute load is higher, and also you need a lot of 24-bit and 32-bit fixed point processing. So you see the HiFis have higher 24-bit and 32-bit processing throughput support as well as higher floating point processing support.
Okay, so Pushkar, what about applications like radar that need to go really fast?
Right. Radar and high-end audio needs even higher compute. So Tensilica has the Fusion G3 processor, which is targeted for such applications. The Fusion G3 is a 4-slot VLIW, and you see the Fusion G3 also has 8-bit processing capabilities along with 16 and 32-bit. So the G3 is a multi-purpose DSP which can be used for moderate compute needs for radar, for high-end audio, as well as for some compute needs which might need 8-bit support for their processing.
Okay, so is that it? Have we topped out on the performance side of things?
Well, there are applications which need even higher processing, and here we are talking about communications applications. The communications processing in today's modems, they need a lot of compute. They are really high compute. For such type of compute needs, Tensilica has the Connex BBE processor family, and there are 3 members in this family, each with increasing computational capabilities. So the BBEs are even wider machines. They are 5-slot VLIW, and their SIMD increases from BBE16 to BBE64, with BBE64 being the widest SIMD of the family. And they have even higher compute capabilities for fixed point as well as floating point. So the BBE64 can sustain a multiply throughput of 64 16-bit fixed point max per cycle and 16 32-bit floating point max per cycle. And then when we talk about vision processing, which is another example of very high compute, the Vision P5 and the Vision P6 DSPs, they are also wide SIMD machines with support for 8-bit computations as well as 16-bit and 32-bit float. And you see the 8-bit computation support in the vision processors is quite extensive because that consumes a lot of processing requirements for vision processing.
Okay, so let's say I want to use one of these Tensilica processors in my next SoC project. Where do I start? I'm not calling up DigiKey, right?
Yeah, so there are a lot of DSPs that we talked about here. But Tensilica has a framework and an easy way to build all these processors and DSPs. So Tensilica has a processor generator framework which enables you to build and configure your DSP. At the heart of it is a common RISC ISA architecture, which is a 32-bit ISA. Starting from that, you can use pre-configured templates to choose one of the specific instruction sets of the DSPs that we talked about earlier, which have been pre-designed for the specific target application needs, as we just saw. You can then configure your DSPs and your Xtensa processor using various configuration options in the processor generator. And then if you want to customize or add something more than the templates or the configuration option, you can customize your processor using the Tensilica instruction extension language, the TIE language, and add your own instructions or your own IOs to meet your application.
Okay, so what about the software development tool side of this? What if, since I'm essentially building a brand new processor here, do I need to update the compiler myself? I'm not exactly an expert in that arena.
That's right. If you have configured your own DSP, then what about the compilers and what about the tools?
Yeah.
Well, actually, the Tensilica processor generator, once you configure your DSP, the processor generator gives you a development environment with automatically generated tools which actually match the DSP that you have just configured. So as a part of your processor generator, you also get the tools bundle, which includes the compilers, the development environment, the debuggers, which actually match the DSP that you just configured. So you can write your software using the tools that you got from the processor generator.
Cool. Okay. So what kind of flavors of DSPs are we talking about here? If I need floating point, what are my options?
Right. So this shows all the options of the floating point DSPs that you can configure using the processor generator. So you have the Xtensa processor where you can configure your floating point, going all the way from the HiFis and the Fusion DSPs that we talked about to the Connex BBEs and the Vision, all with floating point capabilities.
All right, so let's talk about this customization business a bit more. What if these don't quite fit my application needs?
That's a very good question. While we talked about a lot of application areas here, there always are applications which need something different, something more.
Yeah.
And that's where the customizable tie can help you to write your own instructions or customize your own DSP and write your own instructions to do exactly what your application needs. Here's an example. Microsoft, for their HoloLens holographic processing unit,
Cool.
they added their own custom instructions specifically for their application acceleration.
Okay.
So they used the customizable tie option that we just saw earlier of the processor generator, where you write your own instructions which accelerate the processing needed for your particular application. So here is an example where if you have an application which needs more than what the pre-configured instruction sets have to offer, you can go ahead and use the tie language to write your own instructions and accelerate your application. So Microsoft, for their holographic processing unit, they used the tie feature of the Xtensa processor generator to build their own instructions for their specific application needs. For their application, neither GPUs, neither high-end CPUs were the right fit for their energy and compute needs. They used 24 Tensilica DSP cores, and the DSP cores were developed using custom instructions built using the tie feature of the processor generator.
Okay, so earlier you said that the tools were generated, but Pushkar, I'm still a little worried here. Should I be afraid?
That's a good question. If you have a different DSP, does that mean you have a different set of tools? No, that's not true. No matter what specific DSP you configure, you get an Xtensa Xplorer environment, which is the integrated development environment, which is the same for any of the DSPs that you configure. It is an Eclipse-based graphical user interface which allows you to write your code. It comes with an extensive set of software libraries and examples, and a high-performance C++ compiler, which all you can use within the same environment. So the tools know your DSP configuration. They know what DSP you have configured. If you have added any custom instructions, the tools know what instructions you have added, and so the tools are pre-configured for your specific DSP. So no matter what DSP you have configured, you can use the same Xtensa Xplorer environment to do your development, debugging, software development, along with tools for code coverage, profiling, and multi-core support.
Okay, cool. So, Pushkar, let's dive in and talk about the programming model. Is it hard to use?
For programming a DSP, let's talk about the different programming models that one would use. One can start with standard C code and the native C data types. So basically write plain C code and then use the auto-vectorization capability of the compiler to take C code and map that to the optimized code using DSP instructions. One can use operator overloading to optimize code for specific data types. And finally, one can use intrinsics written within C code to use specific instructions exactly controlled by the way the programmer wants to write and optimize code.
Okay, Pushkar, I'm a little in the weeds here, though, with all this VL, IW, and vector, SIMD stuff. it seems like it's a lot to handle. How do we work with this on the programming side of it?
Let's take a look at standard C code. If you have a VLIW machine and if you have SIMD and if you write standard C, then yes, it's a natural question for a programmer to ask on how do I make use of the VLIW and how do I make use of the SIMD? Do I have to remember everything about the slotting, the VLIW, and the SIMD features? Well, here the compiler helps you with the auto-vectorization feature. So if you write C code, here's an example where you write a simple dot product in plain C. You have not used any VLIW or any SIMD instructions yourself. But when this code is compiled using the auto-vectorization compiler, the compiler actually goes ahead and vectorizes this code and uses VLIW and SIMD all starting from just plain C. In this particular example, we have used the Fusion G3 DSP, which we talked about earlier. So this C code, when compiled with the compiler produces optimized code which uses the Fusion G3 VLIW as well as the Fusion G3 vector instructions to bundle and parallelize to give you the most efficient and optimized code starting from plain C.
Okay, cool. So, Pushkar, this was quite a lot to cover today. Can you recap your main points for me?
So what we saw was that most DSP applications need a mix. They need fixed point as well as floating point, and Tensilica processors offer both fixed point and floating point support on Tensilica DSPs. The floating point use in DSPs is increasing. The number of algorithms and the number of applications which need floating point is more. So all Tensilica processors have floating point support, from the low-end processors to the high-end processors. The compute horsepower is very different across applications. So as we saw, there was variable processing with low-end needs, all the way to communications and vision processing with very high-end needs. So Tensilica processors cover the low-end needs and the high-end needs with processors with varying SIMD and VLIW capabilities. Finally, the ease of software development is an important aspect. Tensilica IDE, the Tensilica Integrated Development Environment using the Xtensa Xplorer, and the auto-vectorizing compiler that we just saw give you a very fast and efficient software development environment.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Pushkar.
Thank you very much.
And before we go, don't forget to click that link. There you can find out more information about Cadence Design Systems' fixed point DSP solutions. For Chalk Talk, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the on-demand section on eejournal.com or check out YouTube, keyword EE Journal.